The next and last talk in this session is Connectivity Oblivious Merging of Triangulations by Silva, Schedringer, Etienne, Nonato, Silva, and Comba, and Luis Fernando Maia Silva will be giving the presentation.
Hi, I'm Luis Silva, and I'm here to present the paper Connectivity Oblivious Merging of Triangulations. The motivation of this work is when you have high complex meshes and you want to perform some operations like a merging, you may face some issues. For instance, connectivity and quality of tetrahedral or triangle, depending on our case. And our work, with this work, we could achieve the following result. Here we have the original mesh and another one to put them together and generate a new one. And we had this ending result. And notice that the bigger mesh, it kind of adapts to the target mesh. Okay? So with this work, we achieved the following contributions. We developed a new approach to compute weighted Delaunay triangulation from meshes. We proposed two merging methods for regular triangulations, a mechanism to solve an issue that we had, and I'm going to show you. We call it fringe. It smooths some bad simplices we had, and we applied this method in 2D and 3D examples. Okay, the basis of this work is weighted Delaunay triangulation. We should remember that they are a generalization of Delaunay triangulation, where each vertex is associated to a weight. And the important thing to remember and to point out is that we can change those weights to handle, to force some connectivity, to maintain some triangulation. Here I have some example. I'm increasing the weight of that vertex Si in such a way that I'm gonna force a flip and change in an edge. So we can use it to take a mesh and store that connectivity, and you can even throw the connectivity out and restore it just using a method of weighted Delaunay triangulation. Another property we have to remember is that the triangulation can be defined by the convex hull of those points on the upper envelope. Here we show the vertices. Here we show a vertex. Its position, it's given by their coordinates plus their weights. So we can change those weights to make this vertex up or down at this hull. And this will change our connectivity on the mesh. Some related work to ours are the work of Edelsbrunner, where he exploits this relation between the regular triangulation and the convex polyhedra. Masada, we had another works like Signoni De Floriani, where they proposed a method to keep that information, to define those weights using a linear programming problem. And they solved that problem so they could store that connectivity on their weights. And Balavan and Pires also performed some methods using this particular characteristics of the weighted Delaunay triangulation. So first, we developed a method to compute the weights. And how this method worked, we proposed a new method using lifting points. We had an original triangulation, and then we applied a lifting process to generate that upper envelope. And then we have a mesh with weighted vertices. And then we applied also a subdivision process to have a conformal weighted mesh, because sometimes you face difference between this mesh generated by the lifting process, and we had to use this subdivision process to get a ending mesh which had the same edges and like the original triangulation. Okay, so this is our weighted Delaunay triangulation after we used this conformal weighted mesh to apply our merging mesh. So how we computed those weights? When you have the original mesh, you had two triangles and they share an edge. So we had to set a weight here in order to make it convex. And then when this structure is projected, the connectivity information will be the triangulation that we wanted to keep. So we had to generate this polyhedron to enforce its local convexity. So to have this vertex convex, its weight, it has to be bigger than the necessary when it's on the plane defined by its neighbor. So what we done? We make it equals, we set a weight in such a way that it's on the plane, and we add a small epsilon, so we could force it to be convex. In our method, we use a breadth-first algorithm to assign those weights, and we had to start from a seed. And then we started to propagate that weight, that convexity, from its neighbors. So here I'm showing, imagine this is the seed, so I have to define a weight here, so it's going to be convex, and then here, and after the neighbor from this one and the other one, and so until you reach the border. Okay? But we had some issue with missing simplices. After you set a weight for all those vertices, you can't change it in order to force this simple triangle to appear. And sometimes you can handle, you're going to face missing simplices. How could we solve this problem? First of all, we detect the missing simplices, and we develop a subdivision process. So we forced that particular edge to reappear on the mesh. Here, I show you, on the original mesh, this red edge was present. So we subdivided, force a new vert to appear here, and again, so that we had a conformal mesh. And now I'm going to present the merging of those meshes, and that happens when after you define all the weights. And we merge the mesh T1 and T2. We manipulating the polyhedron generated by our method to compute those weights. So we propose two merging approaches, and they have particular specification. The first one called convexification, and the second one translation. How does the convexification method works? We had to squeeze the lifted polyhedron of the second mesh between the lifted polyhedron of the first mesh. So here we have the first mesh, and here we have the polyhedron of the second mesh. So we had to squeeze it between it in such a way that when it projects to the plane, it's going to be only one mesh. So we detect the simplices of T1 that intersect with the T2 here. And then we project the T2 into the supporting planes of that mesh here. Okay. And we call it convexification because after we had to convexificate that mesh. Here. Had to put it a bit down, so when we project, we had this new mesh. This is the ending result. So those two are going to give rise to a single mesh merged. And then we proposed a new one because that first one we had to change the lifted polyhedron. So it has the issue to make some flips and change that topology. So the second is it tries to keep T2 unchanged. So how we did that? We just don't change that second polyhedron, and we find a way to position it to calculate that distance between T2 and T1 and add it to all those weights. So we just move it on the space in such a way that we have it. Okay, we never change this polyhedron. And we had an issue when we tried to merge meshes with different refinement levels. We're going to see those issues. We had badly shaped simplices, and we proposed this fringe, which is mechanism, to smooth the transition between those meshes. First, we define a regular grid around the mesh we want to merge, and we applied a Laplacian solver to smooth this transition. Okay. Then we create a Delaunay triangulation here, which is the result of this mesh and the fringe. And then we take this mesh and merge with another mesh, the mesh we want to put together. So this make the neighbors with more quality. And results we've got with this work, we used Siegel's algorithm, and we had that epsilon to define the lifted polyhedron, and we could analyze that big epsilons generate more redundant simplices, and the small may cause numerical instabilities. So when we merged 2D meshes, we had a pre-computed animation, and we started to merge multiple meshes. The preference orders depend on the mesh you are putting together. You only merge 2 at a time. So here we have a background, and we add some meshes. Look how the background, it changes. So the other meshes move, and it adapts. Okay. We also compared the merge on 3D meshes, and we applied the fringe to evaluate the performance. So the convexification-based merging, it has the advantage of not generating so bad, so great impact on neighbors. Here, you're going to notice that the next method, it impacts the neighbors directly. Here's the ending result. And see, bad tetrahedra. And we also merged meshes with high quality and a lot of vertices just to evaluate the performance and stability of our method. Here, you can see badly shaped when you have a difference of refinement between those meshes. Here, an approximation. So when you have this case, you can solve it using the fringe. Okay. And we also use this data set where this Buddha, it has no points inside. So here's the bottom of the Buddha touching this cube. And inside you see there's no point. But as we are using the Seagull's method, the method is going to create tetrahedra. And here you see badly shaped. And our method to compute weight, it's really, really fast when you compare to Seagull's triangulation algorithm. So for the grid, the Hawker, over 5,000 points, and it's really fast. So the merging, it's also fast, even compared to Seagull's. And the fringe we use to smooth that transition between the mesh, and it improved the quality of the synthesis. So here's the time we had to compute the fringe. And the result. Notice here some tetrahedra with bad shapes, and after the fringe, so it smooths the neighbors. Conclusions. We defined a solution to compute those weights. Of course, it's not perfect since you have to use that subdivision process, but it's really fast because it's a linear approach, and we use that subdivision to fix those missing simplices. And we used merging methods to handle that connectivity automatically. I just had to deal with coordinates and weights. You don't have to worry about connectivity. It's gonna be stored and rebuilt itself. And that part where one mesh merged with another, it also updates itself, and you don't have to worry about it. It's really simple. About the translation, we had no flips on the main mesh since we didn't change the lifted polyhedron. It affects more the neighborhood because you don't adapt it, and the convexification affects less the neighborhood, but in our worst case, when you change that lifted polyhedron, we could achieve 10% of missing simples. And the fringe, about the fringe, it solved our issue when we were trying to mesh with different refinement levels. It improved the quality of the final mesh at all, but it requires a space to define a good grid depending on those differences. This method, those merging methods, can be used with another method to compute weights, but they fit better for convex meshes since the algorithm to generate will build the whole of those points. And our method is faster than the Seagull's weighted Delaunay triangulation method. The translation-based merging has to find a better convexification to put it on the main mesh. This is a future work. The convexification, we had to improve mainly in the part to squeeze that mesh, because that's when our problems really they actually happen. And we had to study that epsilon, because when it's too big, it gives some problems. When it's too small, it give some problems too. So we should study numbers for that epsilon. Okay. Any questions? Thank you.
So, any questions? This method is only for triangles, right? You cannot do for quads, for example.
For
quadrilaterals, meshes with
but
quadrilaterals.
it works on when you have bidimensional meshes, you're gonna have triangles. But when you're on 3D space, you're gonna have tetrahedra.
Okay, but not quadrilateral. In 2D, you cannot do quadrilateral meshes, quads.
No.
Oh, okay. There are any further questions? If not, let's thank all the speakers in this session. Thank you.
Thank you.